our final speaker today was one of the first people to attend the in-person Kitchener-Waterloo meetup when we still had them before the pandemic. His name is Arun Raghavan. I hope that's didn't butcher it too much, but he recently moved to the KW area and is a contributor to GStreamer. He joins us today to give an introduction to GStreamer.
Hey.
Go ahead.
Hey, thanks for the introduction. Are my slides visible okay?
Yeah, I can see him.
Okay, perfect. Okay, hey everyone. Thanks for making it to this. So I'm Arun. That's my GitHub / Slack profile and my Twitter ID and email. I run a small consulting company working on open source software, all sorts of low-level system stuff, particularly multimedia. And I'm just going to go through a quick introduction of GStreamer. I'm not going to walk you through a lot of detail right now, but hopefully it gives you a flavor of about the project that I quite enjoy contributing to. Right, so let's jump into it. What is GStreamer? GStreamer is basically a library for building multimedia pipelines, right? So if you're building an application that deals with audio, video, or both in any form, it's not a very novel idea, but it is a pretty powerful idea that you might want to model your flow of audio, video, or whatever as a data processing pipeline, right? So GStreamer allows you to build and express the multimedia part of your application as a pipeline. Right. And before we go into details of where it's used and what kinds of use cases you can realize, I thought it might be fun to jump into what these pipelines actually look like. Right. So we have a, if you're using GStreamer, there's a command line prototyping tool for building pipelines called GStLaunch, and that allows you to write these pipelines and test them before you might want to convert them into code. Right. So let's say we want to make a toy pipeline to read an MP3 file and play it out. Right. So I might start with a file source element, right? In GStreamer, you have the notion of elements, which provide a sort of unit of functionality. So the file source element provides the ability to read data from a file and pass that on. And this bang operator that you see, the exclamation mark, allows you to connect to elements, right? So we connect the file source element to the an element called Mpeg 123 audio decoder. So this is a little element that wraps the MPG 123 library and provides the ability to decode MP3 frames. So so that you can then connect the decoder element to something that does, say, some audio conversion. So maybe you won't need to do format conversion or upmix, downmix number of channels to actually play it out on your local system. And say you're on Mac OS, you might use the OS X audio sync element, which consumes data and renders it out. Right? So diagrammatically, this might look something like this. So you have the file source element connected to your Mpeg 123 audio decoder. So the file source is reading data from the file system and passing buffers on to the decoder element. The decoder element is taking MP3 samples, using the underlying library to do decoding and pass PCM samples to audio convert, which can do some negotiation to understand whatever it needs to pass it on to, what format is required. So it'll do, say, converting, for example, say flow 32 little endian audio from the decoder to, say, sine 16 little endian audio for the actual device. And then you have the sync element, which might then take this and render it out using your operating system's audio services, right? So, so you can see there's a source element that provides data, there's some transformation happening, and there's a sync element that consumes data and does something meaningful with it, right? So that's our pipeline. Any questions around this? Does it all make sense? I'm going to actually assume, since this is sort of time limited, I'm going to leave the questions to later, but feel free to throw them out in chat and we can address them. Right? So this is a very simple pipeline. Let's make it a little more complex. Right? Suppose we want to consume data from somewhere on the network over HTTP. We know it's data in an MP4 container. It has AAC audio and H.264 video. And let's say now the application that I'm building is actually on Android. Right? So I want to now render this. Again, this is playback on Android. So here I might, instead of the file source element, I might use the soup HTTP source element. And this is an element that wraps the libsoup HTTP library and provides a source that can take an HTTP URL, read data from it, and just provide it. Right? And I then connect that to my Qt demux element. So this is Mpeg for format demultiplexer. So this it's named this way because it's from a time when QuickTime was the implementation of MP4 and before the ISO Mpeg-4 standard was formalized, I think. And yeah, and what we're doing here is this demuxer element is going to read the MP4 stream and then say, okay, this stream has some actual audio and video streams inside it. In our case, it has one audio stream and one video stream. And so it's going to produce two outputs, two separate outputs for this. And this is different from our previous case where each element along the path had only one input and one output. So we have the audio part of our pipeline and the video part of our pipeline that we now need to deal with, right? So the audio part might go to, say, another element. In our case, we want to use the Fraunhofer FDK that provides AAC decoding. We have an element to wrap that, and we decode it on the CPU and send it out to the Android audio subsystem using Android's native audio layer, which OpenSLES being one of them, right? So we basically have this audio pipeline going out. And things get a little more interesting when you want to deal with video, right? So if this is running on Android, presumably this is on a mobile device where we want to be power efficient, right? So we want to use the underlying hardware's and platforms' ability to provide accelerated video decode services. And that's usually a decoder block alongside the GPU. And we also want to render it without having to take that memory from that decoder block back into the CPU and then give it back to the GPU again. So we want to set up an efficient pipeline that does the decode and render without pulling the data back into the CPU, but while still possibly adding, knowing that there is such data flow happening and being able to kind of control and synchronize it and things like that, and maybe even apply transformations within the GPU. So how we do this is that, so we've got Qt demux that provides the video frames one at a time, and there's a GStreamer element that wraps the Android media codec APIs, which are the sort of official Android API to access the platform's video decode capabilities. So we use the AMC video deck, Android media codec services to perform the decode, and we get a handle into some memory that's not in CPU, and we can hook that up into an OpenGL ES sync, which needs to be initialized with the correct parameters to render into some part of our UI. But assuming we've set that all up, we now have an efficient pipeline to decode and render this video, right? So this is what video playback from the network might look like. And by this time, it might seem like this is all a bit cumbersome, and you might not want to do this for your application, right? I mean, what if this is Matroska and not, or WebM and not MP4? And what if it's VP9 and not H.264 and all of that? So we have conveniences on top of this, right? So these are the building blocks, but you might want to have something simpler where you take a file source which reads data from a file and gives it to a decode bin, a bin being a higher level element effectively that can wrap a bunch of smaller elements and provide a higher order functionality. And in our case, what Decode bin does is it'll go look at the registry of GStreamer plugins, look at the data that's coming in, and just try to decode it for you, right? So without you having to worry about the details of setting up the internals of that pipeline. And you can take that the output of that. So if Decode bin is able to decode MP3, you'll get PCM data on the other side. And you can use another bin called Auto Audio Sync, which correctly picks out the correct sync for your platform, right? So whether we saw that for macOS we had a different platform, for Android we had a different sync, and for Android we had a different sync. So this takes care of all that magic for you, right? So that's allows you to think about this in higher level terms and not worry about the details necessarily. You might want to zoom out even higher and say, hey, I have a URI, I want to play it. So we have this notion of a Planeman, which abstracts out the common playback use case of I have a URI, I need to play it efficiently on my platform, figure out the appropriate syncs to use. I can set them up if I want to. I have a bunch of toggles for dealing with, do I want to show subtitles or not? Do I want to have volume controls, etc.? So giving you a higher level API into this sort of thing, right? So that's just a flavor of the simple playback use cases of with GStreamer and what it looks like when you're looking at it in detail, and the kinds of abstractions that we provide on top of all those details. So why might you want to consider GStreamer for some of your use cases? As you can see, it's quite flexible, right? So we have all these small elements that you can compose together to use in different scenarios. So in our case, for example, the Qt demux that deals with demuxing Mpeg for container formats doesn't care about where the data comes from, right? It could be a file source, it could be HTTP, it could be anything, right? And like that, the decoder doesn't care where the data is coming from either. And so we're able to compose these things together to build different kinds of different kinds of pipelines for different kinds of use cases. Let me talk about that a little more. It's extensible. So if you notice, we had 3 different kinds of elements wrapping 3 different kinds of decoders. And so if you, for example, had your own library to deal with a specific codec, you could bring that into your application, wrap it in a GStreamer plugin, and we have a lot of convenience APIs to make that easier. And you could use all this flexibility while having custom bits of functionality that you want to implement by yourself. So that could be in the form of transformations, encoders, decoders, post-processing, all sorts of things, right? Sources and sinks that to deal with your specific use cases. So there's extensibility. I've already alluded to GStreamer being cross-platform. So it works on desktop and embedded Linux, Android, of course, macOS, iOS, Windows on desktop and mobile. So there's that aspect to it. And GStreamer itself is written in C. The project's been around for over 20 years now. So, but it's based on a framework called glib and gobject, which gives some object-oriented features on top of C, and also gives you an easy way to create bindings to languages like Python, JavaScript, Rust, Java, Haskell. We have bindings for all of these things, and so we're able to use this functionality from other languages as well. Okay. So where is GStreamer used? If you're using a Samsung Tizen TV or an LG WebOS TV, you're already using GStreamer. A number of platforms that ship speakers based on Alexa voice services. Or even the AVS SDK, the Amazon AVS SDK uses GStreamer as sort of the platform enablement layer. There are security cameras and video conferencing cameras that use GStreamer for streaming and things like that. So which ties into real-time communication. So you have GStreamer that is used in, there's the Currento media server and various other client and server use cases where GStreamer gets used. The Mozilla Servo project, as well as WebKit, there are WebKit ports that use GStreamer. So you have embedded devices that might want to use HTML, CSS, and JavaScript to draw their UIs, but use platform facilities to do accelerated decode and render and things like that. So WebKit GTK has ports to various embedded platforms to be able to use that kind of functionality. The BBC and several other broadcasters use GStreamer in their broadcast and other parts of their data processing pipelines. You have automotive use cases, in-flight entertainment, even Japan's I think it's called the Aeronautical Exploration Authority, had a little robot that went to the International Space Station, and that was using GStreamer for capturing from its cameras and streaming out over the network. So there's a lot of different types of use cases in which GStreamer gets used, right? And that includes playback and capture. We've already seen what playback might look like, but capture could be something like having a capture from a camera, maybe having that efficiently be encoded on the GPU, getting those H.264 frames, for example, streaming it out over the network, but also saving it locally to a file. Those sorts of things can be built. We have support for RTP, HLS, and Dash, both as servers and clients. Right, so there's that kind of functionality. Of course, you can encode and decode and transcode using existing libraries, using your hardware's capabilities. So that's one other whole class of use cases where GStreamer finds use. There's an entire nonlinear editing library that's built on top of GStreamer, and that's like a whole project in itself that gets used. It's called GStreamer Editing Services, and there's a lower level library called GNonlin, which basically provides these kinds of functionalities. There is a WebRTC stack that is written in GStreamer. So there's a GStreamer WebRTC library, which pretty closely mirrors the WebRTC RTC peer connection API. So it's very closely mapped to make it easy for folks to build WebRTC applications on top of GStreamer. And this can be quite handy if you're using WebRTC on certain platforms and you want a degree of flexibility and customizability that the Google WebRTC library does not always provide, right? That being the sort of canonical go-to implementation for a lot of people. We do synchronized playback. So if you have, I already spoke about automotive and in-flight entertainment cases, but even, you know, the advertising space or in just out-of-home displays and things like that, you might want to play the same video and audio stream across multiple devices and have them be played in sync. That's something we have libraries to make it easy to build those sorts of systems that are sitting on top of GStreamer. People use GStreamer for computer vision stuff. So we have elements wrapping desktop and embedded GPU functionality to deal with computer vision processing, and basically all sorts of data processing is quite easy to realize with GStreamer. So in fact, the GStreamer code does not make any assumptions about dealing with multimedia. So it's written in a sort of fairly agnostic way of what the underlying data is. So as an example, the LIGO project to detect gravitational waves use GStreamer for their data processing pipelines. Right? So that's roughly all I had with regards to what GStreamer is, what kind of features it brings to the table, a very quick flavor of what thinking in GStreamer terms looks like when you're talking about pipelines. I've seen one, I think a lot of folks that hang out, especially on the video dev Slack, are quite familiar with Fmpeg, and I've heard some questions about, you know, are these competing projects or how do they work together? And both these projects have a pretty good working relationship and do interoperate. In my head, I look at GStreamer as sort of a high-level toolbox for building multimedia applications. Whereas Fmpeg gives you a lot of very powerful lower level tools to deal with codecs, formats, and things like that. So in fact, the GStreamer comes with a whole set of plugins that wrap the Fmpeg library and provide a lot of important and even niche codec decoders and encoder wrappers, as well as parsers and things like that. So if anyone was wondering about, you know, how these projects coexist and sort of what you might want to use for what, that's kind of meant to clarify that. And I realized this was a very quick rush through the subject, but yeah, I'm happy to take questions and happy to do talks maybe in later sessions if we want to go into details of any particular area of this. Yeah, thanks for listening.
Thanks, Arun. That was a great talk. I had a couple of questions. If anyone has any questions, you can just go ahead and type them into the chat. You mentioned the Android SDK a bit. Now, is that like just something, or just Android? Is that something that you'd have to install separately when you like deploy your app to use GStreamer, or is GStreamer natively available?
It's not natively available on Android, so you'd basically have to include it as a library in your app.
Oh, okay. Okay.
Right. So we give you some sort of like tarball that you, with the libraries that you can link into your application and use it.
I guess a follow-up would be, you mentioned a ton of codecs. Does it support like libx264 or QuickSync or NVEnc as
so
plugins?
x264 is definitely there. I think, so what were the other two?
QuickSync, the Intel hardware acceleration.
Yeah.
And the NVIDIA hardware
Yes.
acceleration.
So NVIDIA provides some stuff for at least on embedded on the embedded side. On Linux, I think I'm not sure about where the current thing is, but I do think we have NVEnc wrappers. For QuickSync, Intel has this Media SDK, which I think which is also a cross-platform way to access their hardware encoders and decoders, and we do have plugins around that. And now that I remember, I'm pretty sure we do have wrappers for NVEnc as
well. Yeah, that's it for me. Did any other participants have a question?